Hey guys, um, so I'm going to record these videos here. The best spot I found is a Panera, um, so I apologize for that. Hopefully the ambient noise just adds to the experience. So what I want to do in these videos is go over how to apply our recipe for electric fields to continuous distributions, much like we've been doing. And so I want to go through the different examples. I think I'm going to break them up one video for each example. So I'll review a ring of charge like we did last time in class. Then we'll do a disk of charge. Then we'll do, a line of charge. That's probably about what I have energy for. Okay, so that's the stuff that I was hoping to go over on Thursday and wasn't there for. All right, so before I really get into it, let's kind of go through the recipe for how to cook up electric fields. All right, so the basic steps. So first off, as you guys have seen, the shape determines so much in terms of our strategy, like the exact formulas we use, and so our choice of coordinates, things like that, which is our second choice. Then after you choose coordinates based on the shape, we want to express, I said differential geometry, but really I just mean figure out, how to write DL or DS for arc length, dA for areas, or dVs for volumes, although we're not going to do one of those today. And then once you have that, use the appropriate type of density. So if it's a 1D shape, use lambda for linear density. If it's a 2D shape, use sigma for surface charge density. If it's a 3D shape, use rho for volume density. And then combine those with the differentials to get dQs. So for example, let's take the example we're going to talk about today, or first here. Let's say we had a, get my stylus working. What's going on? Try that again. So let's say we've got a ring. Okay. So the shape, it's round, and it's a 1D shape because I can parameterize a ring just by specifying one number, the angle or arc length. Choosing coordinates, we're going to use r theta. Really, r is frozen, so I'm going to write that as a capital R. It's not really even a coordinate, it's just a fixed parameter, but that's okay. Express the differential geometry in these coordinates. Well, the appropriate differential geometry would be arc length. So if I can kind of indicate a little segment there, we would say that ds is r d theta. And then label a little bit of source charge. So here's my little segment. I would have a little bit of charge, dq. Right, that's what a little segment would have. A little bit of charge has charge dq, and I would want to rewrite that in terms of geometry stuff. So I'd say dq equals lambda ds. So I'm saying every little bit of arc length gives me a little bit of charge, and the factor that makes that happen is the linear charge density. And then I could write that as lambda r d theta. And that's where what should go down here for dq. Okay, so, and then I would express RO, the position of the observer, position of the source of a quote unquote typical bit of charge. So choose something out in the middle of the shape. Don't choose an edge or a funny corner. And that way the formulas you write down are kind of arbitrary. And then work out RSO, magnitude RSO hat, all those things. And then work out for E. So The physics formula for E is always integral 1 over 4 pi epsilon naught integral dq over magnitude RSO squared R hat SO. That's the physics formula. Then you have to mathematize it. So you have to substitute in for dq, for RSO, all that stuff. And then do the math, do the integral. That's the recipe. It's always the same. Certain shapes, sometimes you can look at it and just skip small steps in here, but if you follow this recipe, you'll always get it right because it just forces you to go through every little wrinkle, every possible option. So let's do a simple shape. This is the same one we did in class on Tuesday, but hopefully it'll kind of illustrate these steps. Okay, so the electric field above a ring. So let's be a little bit, let's see, let's imagine I've got a ring of charge in the XY plane, and I would like to know what is the electric field at a height Z above the center of it. So this is in the XY plane, that's fine. So it's a 1D shape, it's a ring. I know I choose coordinates. My coordinates are going to be as before, R and theta. And then I know that arc length, ds, so if I kind of had a little segment of the ring, the arc length would be r times d theta. And then dq, the charge carried by that little segment, would be the linear charge density multiplied by r d theta. I have some stylus difficulties. Okay. Now, next up, to mathematize this shape. So what I'm going to do, so it's clear that the observer, that's way up here on top. That's going to be z hat. That's easy. What about this little segment? So let me kind of dot in. Assume that's the x and y direction. A little dot here. What we need is a vector from the origin out to this segment. And remember, I just chose a typical segment, nothing special. So here's theta is supposed to be with respect to the x-axis. So that means this is theta. If I think about it, the x component is going to be adjacent to theta, and the y component is going to be opposite theta. So I can write RS for that little bit of source charge is R cos theta x hat plus R sine theta y hat. Okay, remember, so next up we want SO. It's important that you remember that that's RO final vector minus initial. So that's going to be z hat minus R cos theta x hat minus R sine theta y hat. Okay. All right. Now, okay. We can work out the magnitude. Sorry. Magnitude is, so I take the square root, and it's going to be the z component squared plus the y, or the x component squared plus the y component squared. And using the Pythagorean identity. This is z squared plus r squared. Okay, piece of cake. And then, okay, which just, you know, small town, not much to do. Why don't we write this like so? Oh, to the, sorry, I guess this just be to the 1/2. All right. Then the unit vector RSO hat is simply RSO divided by the magnitude RSO. If you think about that, it'd be z hat minus r cos theta x hat minus r sine theta y hat, all divided by z squared plus r squared 1/2. It's a slog, I know, but it's always the same slog. So once you get the recipe down, just kind of make it a routine. It's mechanical. You just go from thing to thing to thing. Okay, now Coulomb's law says for a point charge, says that the electric field from a point is 1/4 pi epsilon naught times the charge, let's just use the charge of the source divided by RSO magnitude squared times the unit vector r hat SO. When we, our strategy for dealing with continuous charges is to take the smooth distribution, in this case, it's this ring, and then use the magic of color, maybe. That must be above my pay grade. Oh, here we go. And then we use the magic of color, and we say, oh, well, apparently that's just too much for me. Okay, and then think of that ring as a whole bunch of little point charges. Now, the total charge, and I should have said this from the beginning, and I apologize. Like on Tuesday, I'm going to assume that the charges spread uniformly over that. So we think of this continuous distribution as if it is a collection of point charges. Okay, so each point charge gives it's just a tiny bit of charge. It's not a macroscopic number, it's a microscopic number. So we get a differential amount of electric field from each little point charge, which has a differential size. So it's really the same formula. You're just applying it to a baby step, a baby chunk of charge. Okay. Again, we're going to assume, I should have said this before, that the charge density is constant. It just changes the calculus a little bit. You'd have to do some integral. It's not quite as trivial. All right, so let's set this up. I'm going to write, as I frequently do, I'll say something like the total charge is nothing other than the sum of the charge density, sorry, let's do this, of all sum of all the little charges. That means it's the integral of lambda ds, which is the integral of lambda r d theta from 0 to 2 pi. You can check that that is 2 pi r lambda. All right. Similarly, when I write another trivial statement, I'm going to say that the total electric field is what you get by adding up, using the superposition principle, all of the baby electric fields. But those are going to be expressed in terms of charge. Okay, we're not quite ready to pull the trigger and do this integral because I'm integrating here over charge, but I've got geometry stuff. So I need to turn charge into geometry. Again, I'm going to use the density as before and say that the electric field is the integral of 1 over 4 pi epsilon naught. That all pulls out. dq is lambda r d theta as before. The magnitude of RSO we worked out before, that's going to be z squared plus r squared. Now, the magnitude just was to the 1/2 power, but I've got the magnitude twice here. So think of that as 2 halves. And I have the unit vector. Oh, so there we go. So that's a z hat minus r cos theta x hat minus r sine theta y hat. Forgot my hat on there. Okay. Divided by z squared plus r squared to the 1/2. So now, first thing to note is that many of these pieces do not depend upon theta. Theta runs from 0 to 2 pi around the circle, and especially the denominator. So I can pull out constants. So that's going to be lambda r over z squared plus r squared. So 3 halves times the integral d theta from 0 to 2 pi z hat minus r cos theta x hat minus r sine theta y hat. Okay, now, if you look at this, I'm integrating over theta. These, lambda, r, z, those are all constants in this problem. You know, they're written as, there may be unknown constants. So they're written as symbols. They're not varying as we move around the ring. The only thing that varies is theta. So you think about it, you're going to end up with an integral over cosine. That's 0 as you go all the way around the circle. And this integral over sine, that's also constant as you go around the circle. So the only thing, kind of here, the pieces, so this bit and this bit are going to integrate to 0. The only piece that survives is the first piece, which for us is completely independent of theta. So it's super easy. It's an integral anyone can do. So the electric field we calculate is simply 1 over 4 pi epsilon naught lambda r over z squared plus r squared to the 3 halves. Now what happens with this integral? Well, the constants come out, so I can write z hat, that's a constant unit vector, but it's still constant. And I'm left with just an integral over theta from 0 to 2 pi. That's just times 2 pi. Nice. And we immediately see that clearly the pretty way to regroup this is to combine lambda r and 2 pi together, because those just come together to equal the charge. Remember, that's what we had up here. 2 pi r lambda is the charge. So my final answer for the electric field, the distance z above a ring lying in the xy plane is and there you go. And that should match what we did on Tuesday. Okay, so I'm going to stop this video here, and then next I will perform a very similar calculation to find the electric field above a ring. And then not only will we do that, we'll also take the limit as the ring, or sorry, not the ring, the electric field of a disk. And then I will also take the limit as that disk gets to be infinitely big, and we will learn about the electric field of an infinite plane of charge. Okay, see you next time.